Hi, my name is Abhishek Singh Kushwaha. I am a master candidate at Florida Atlantic University.
Hi, my name is Akhilesh Singh Kushwaha, and I am pursuing computer science at FAU. So, today our topic is enhancing multilingual digit recognition, investigating AlexNet, VGG16, ResNet 50, and LeNet on the MNIST-MIX dataset. So, these are the contributions made by each team member, which we have listed in this slide. So, coming to handwritten digit recognition is a fundamental task in computer vision with diverse real-world applications. The MNIST dataset has been popular for benchmarking recognition models, but its simplicity is inadequate for evaluating modern deep learning architectures, achieving over 99% accuracy. So, there is a need to explore more challenging datasets that better represent real-world scenarios. Additionally, the extension of handwritten digit recognition to multi-language settings remains largely unexplored in this literature, presenting an open opportunity for further research and development.
In the existing approach, currently in the baseline paper, we have the LeNet model implemented, which is initially designed on MNIST. It consists of 7 layers, incorporating convolution, pooling, subsampling layers, followed by fully connected layer and an output layer with softmax activation function for class prediction. LeNet achieves a test accuracy of 99.26 after training on original MNIST dataset. After initial training, network connections are frozen and only the output layer are fine-tuned for each dataset. In MNIST-MIX, the output layer size is adjusted to 100 classes. Fine-tuning allows LeNet to adapt dataset characteristics, optimizing performance for multi-language handwritten digit recognition.
So coming to the limitations, these are the two limitations which are limited model comparison, which is only compared with LeNet, and imbalanced class distribution. It is related to MNIST-MIX, which has a imbalanced class distribution. Then,
In this paper, we have proposed 4 other deep learning architectures. Those are AlexNet, VGG16, and ResNet 50. Our focus is comparing these 3 models on MNIST-MIX dataset to understand their effectiveness for multi-language digit recognition tasks along with the LeNet, which is implemented in baseline paper. Through this evaluation, we aim to provide insights into the performance of these state-of-art algorithms.
so coming to the dataset sources, these are the 10 dataset sources which we have mixed into MNIST-MIX. And coming to the data processing, these are the datasets used. We utilize the MNIST-MIX dataset, which consists of 13 different datasets covering 10 languages. The languages represented are Arabic, Bangla, Devanagari, English, Farsi, Kannada, Swedish, Telugu, Tibetan, and Urdu. So coming to the standardization of format, these are the steps to ensure the uniformity and compatibility with MNIST format. First step was converting RGB to grayscale. So images originally in RGB color spaces are converted to grayscale using specific formulas. And pixel intensity calculation, we took the weighted sum of red, green, and blue channels. And the resulting grayscale images were intensity ranges from 0 to 255. And then we resize the images and set the standard size of 28 by 28 pixels using bilinear interpolation. The purpose of this was to ensure consistency in image dimensions across all datasets. Then comes the split. The splitting the datasets into training and testing sets, we have used 80 and 20%, 80 for training and 20 for testing. So this is the image we have coded and extracted from each dataset. So coming to the LeNet implementation, we initially uh, the LeNet model is a train on original MNIST dataset to establish a baseline performance and achieved a test accuracy of 99.26. So after that, the training process involves optimizing the model parameters using the Adam optimizer with a learning rate of 0.01. Categorical cross entropy loss is used as a loss function. Early stopping is implemented to prevent overfitting during the training. So after the training on MNIST, the network connections are frozen and only the parameters of the output layer are fine-tuned for each individual dataset. Additionally, for MNIST-MIX, the output layer size is adjusted to accommodate the 100 classes present in the dataset. So this is the LeNet architecture representation. Coming to the AlexNet. So AlexNet undergoes a training on MNIST dataset as well to establish its baseline performance. And in this, we achieved a test accuracy of 98.50%. We use the Adam optimizer with a learning rate of 0.001 and we optimize model parameters, then minimizing categorical cross entropy loss during training. Early stopping techniques are employed to prevent overfitting and ensuring robust generalization. Then training on MNIST, we fine tune the applied solely. If fine tuning is applied solely to the output layer parameters for each specific dataset. And notably, we made some adjustments are made to the output layer size to accommodate dataset with varying number of classes, such as MNIST-MIX, enhancing the model adaptability across different datasets. So this is the AlexNet architecture.
So in this paper, I have implemented VGG16 architecture. On the right side, you can see the architecture of VGG16. Initially, it was trained on original MNIST dataset to establish its baseline performance and achieve accuracy of 99.11%. The training process involved optimizing model parameters using the Adam optimizer with a learning rate set to 0.01. Categorical crash entropy loss is utilized as optimization criterion during training. To prevent overfitting, early stopping mechanisms are used similar to the previous two models. After completion of training on MNIST, we froze the network connections and only the parameters of the output layer are fine-tuned for each specific dataset. Notably, adjustments are made to the output layer size to accommodate the dataset with different number of classes, such as MNIST. And in ResNet, the architecture is little bit deeper compared to other models. So on this dataset, we achieve an accuracy of 98.15% on MNIST dataset. So and Adam optimizer with a learning rate of 0.01 optimizes model parameters using categorical cross entropy loss during training. Early stopping prevents overfitting. We use this method in this implementation as well. After training on MNIST, output layers are fine-tuned for each specific dataset, and for MNIST, we size the output layer to class 100. For evaluation metrics, we use accuracy. This measures the percentage of test samples correctly classified. And for weighted F1 score, it is the average of the F1 scores for each class, means the number of true samples for each class. And the balance accuracy is the average of recall obtained on each class. Similar to accuracy, its optimal value is 100% and the worst is 0%.
So coming to the results, LeNet results. In this, Adris, MNIST, and MadBase demonstrate exceptional performance across all languages, indicating their suitability for specific tasks. And the LeNet model achieves the highest accuracy of 99.44% on the MNIST dataset, which is an extension of MNIST as well. For MNIST-MIX dataset, the LeNet model achieves an accuracy of 89.90%. However, the balance accuracy for MNIST-MIX drops to 84.47 at the end. Then AlexNet. In this, the same three demonstrates best performance across all the languages, indicating their effectiveness. AlexNet model achieves highest accuracy of 97.75% on the MNIST dataset. Similarly, we told that MNIST is an extension of MNIST, so showcasing its robust performance in recognizing English characters. In terms of MNIST-MIX dataset, the AlexNet model achieves an accuracy of 47.98%. However, the balanced accuracy for MNIST-MIX drops to 19.1717 at the end.
In VGG16 results, the address EMNIST and MATBase shows exceptional performance across languages, showcasing the suitability for specific tasks. The VGG16 models achieve the highest accuracy of 98.50% on the EMNIST dataset, indicating strong performance on English characters. For the MNIST-MIX dataset, the VGG16 model achieves an accuracy of 66.56%. However, the balance accuracy for MNIST-MIX drops significantly to 40.24%. In ResNet 50 results, similar to VGG16 and other models, these three datasets shows exceptional performance across other languages. ResNet 50 model achieve an highest accuracy of 98.44% on EMNIST dataset, indicating strong performance of English characters. And for the MNIST mixed dataset, the ResNet 50 model achieves an accuracy of 53.22%. However, balance accuracy for MNIST mixed drops significantly to 24.52%. Overall, the comparison of all the models shows that at-risk EMNIST and MATBase consistently display exceptional performance, suggesting their effectiveness for the specific task compared to other languages. All the models achieve the highest accuracy on EMNIST dataset, indicating robust performance in recognizing English characters. However, when tested on the MNIST mixed dataset, all models experienced a notable decrease in accuracy and balanced accuracy, suggesting challenges in recognizing digits across multiple languages and diverse writing styles.
So, in conclusion, we used MNIST-MIX, a multilingual recognition dataset compatible with the original MNIST format. So, along with that pre-trained LeNet model, we evaluated VGG16, ResNet 50, and AlexNet. MNIST-MIX expands evaluation scope, whereas the models provide comprehensive performance insights.
That's it for this presentation. Thank you.